Hello everyone. Today I want to give a brief introduction to Machine Learning Interatomic Potentials, or MLIPs. The main topic of this talk is how the field evolved from handcrafted descriptors to modern equivariant graph neural network. The goal of MLIP is to approximate the potential energy surface of atomic systems. Mathematically, we want to learn a mapping from atomic coordinates to total energy, like this. Once we have the energy, we can compute forces using this formula. At first glance, this may look like a standard regression problem, but there is a major difficulty. The model must satisfy several physical symmetries. First, translational invariance. If we move the entire system together, the energy should not change. Second, rotational invariance. If we rotate the molecule. Second, rotational invariance. If we rotate the molecule, the energy should still remain the same. Third, permutation invariance. For example, if we exchange two identical hydrogen atoms, the prediction should not change either. Another important assumption in almost all MLIPs is locality. Instead of directly predicting the total energy from all atoms simultaneously, we use decomposed the total energy into atomic contribution. Each atomic energy only depends on its local environment with a cutoff radius. This assumption is extremely important because it makes large-scale simulations computationally feasible. The first paper I want to discuss is Behler-Parrinello neural network from 2007. This is one of the foundational work of modern MLIPs. The key idea is very simple but extremely influential. Instead of fitting the entire molecular structure directly, the total energy is decomposed into atomic energies. Instead of directly using atomic coordinates for fitting, they choose to first construct atomic descriptors and then perform fitting. For each atom, the local environment is converted into a set of symmetry functions using denoted as GI. Then a neural network maps. Finally, all atomic energy are summed together. This architecture solves the permutation problem naturally because atomic with the same chemical environment share the same neural network. Now the next question becomes, how do we design this symmetry function? They must satisfy translational, rotational, and permutation invariance. To define local environment, the paper introduced a cutoff function like this. This means atoms beyond the cutoff radius are ignored. One important point is that this approach still relies heavily on handcrafted descriptors. In the other words, humans manually design the features first and then machine learning is applied afterward. Next, I want to discuss the Gaussian approximation potential, or GAP, proposed by Bartok and collaborators in 2010. Composed with Behler-Parrinello, this work moves in a different direction. Instead of neural networks, it uses Gaussian process regression. The total energy is written as. The first step is constructing a local atomic density around each atom. This density function automatically satisfy translational and permutation invariance. For example, if you move a molecule from here to here, the relative positions of the atoms in the molecule do not change. Similarly, if you swap two identical atoms, the result remains unchanged due to the commutativity of addition. The next challenge is rotational invariance. To solve this problem, the authors map the three-dimensional environment onto a four-dimensional hypersphere. The main motivation is that after the mapping, the problem becomes purely angular. Then the density is expanded using hyperspherical harmonics. However, the coefficients still change under rotation, so we need rotational invariance. The simplest environment would be something like the square of C, but this loses angular correlation information. To preserve more geometry information, the paper introduced the bispectrum expansion. The bispectrum couples multiple harmonic coefficients together using Clebsch-Gordan coefficients. Conceptually, this captures correlations between different angular components. This is extremely important because it allows the descriptor to distinguish different local geometries more accurately. Finally, the bispectrum coefficients are flattened into a vector and used for Gaussian process regression with a Gaussian kernel. One very important historical point is that many later equivariant models inherit ideas from this line of work, especially spherical harmonics and angular momentum coupling. Now we move SchNet from 2017. This paper represents a major translation from graph network. The main steps of graph neural networks are message passing, message aggregation, and we will see later why these steps are important. The core idea of this work is continuous filter convolution. Each item have a feature vector, and the update rule is this. Here, WL is a neural network that generates filters from interatomic distance. This equation can be interpreted as message passing. The message from atom G to atom I is like this. Then the messages are aggregated by summation. This summation operation naturally guarantees permutation invariance because changing the order of neighbors does not change the result. Compared with Behler-Parrinello, SchNet no longer relies on manually designed descriptors. Instead, the model learns representations automatically. This is one of the most important conceptual shifts in modern MLIPs. However, SchNet still has a limitation. It only uses distances. As a result, angular and geometry information may not be represented efficiently. This limitation motivates the development of equivariant models. Another important work is Deep Potential from 2018. The key idea here is constructing a local coordinate system for each atom. Instead of relying entirely on invariant descriptors, the model transforms neighboring atoms into local coordinates. Intuitively, this is similar to a person observing a bag in their own coordinate frame. If a person and the bag rotate together, the relative geometry remains unchanged. Permutation invariance is handled by sorting neighbors according to atom type and distance. This method becomes extremely influential in large-scale molecular dynamics simulations because of its efficiency and scalability. Finally, I want to discuss NequIP from 2022. This work introduced E3 equivariant graph neural network into MLIPs. Before discussing the model, we should first distinguish invariance and equivariance. Invariant means the output does not change after transformation, and equivariant means the output transforms in the same way. Energy is invariant and rotation, but forces and dipole moments are equivariant because they rotate together with the system. The key innovation of NequIP is replacing scalar features with geometry tensors. Node features are written as like this, where L correspond to scalars, vectors, and higher order tensors. Message passing now explicitly includes spherical harmonics. Here R is a radial neural network, Y are spherical harmonics, and V contains tensor features from neighboring atoms. Angular momentum coupling is implemented using Clebsch-Gordan coefficients. One important idea here is that NequIP does not discard directional information too early. Instead, geometry information is preserved throughout the network. This significantly improves data efficiency and force accuracy. To summarize, the development of MLIPs can be viewed as the evolution of geometry representation. Behler-Parrinello relies on handcrafted invariant descriptors. GAP introduced harmonic expansion and bispectrum descriptors. SchNet introduced message passing graph neural networks. Deep potential use local coordinate systems. Finally, NequIP introduced E3 equivariant tensor representation. Overall, the field has evolved from manually designed symmetry functions toward fully geometry and equivariant neural network. These are references. Thank you.